Hello class, welcome to lesson 5.4. So we're going to talk about inequalities in a triangle. So our essential question today is, what are the relationships between the sides and angles of a given triangle? So we want to use theorems to compare sides and angles of various triangles as our goal today. So we are given two triangles here, and what we want to do is we want to be able to rank the angles and the sides from greatest to least. And this is going to help us to determine if there's a relationship between the angle measures and the side lengths of a given triangle. So let's go ahead and start with the angle for the top triangle. Now this is an obtuse triangle, meaning one of the angles is actually an obtuse angle. That's going to be angle X here. That's an obtuse angle. So we know that this is going to be larger than any of the other angles in this triangle. Now looking at this triangle looks like it's slightly bigger than this triangle in measure. So what we have here is that the smallest is angle Y, the second smallest is angle Z, the largest is angle X. And so if we were to label it in order, it would go X, Z, and Y. And then here are the angle measures given. So these are actual angle measures that were measured. So 35 degrees, 125 degrees, hence the wide Z obtuse triangle, and then 20. Now for the side lengths, we notice that Z looks like the smaller side, Y looks like the second smallest, and then X looks like the largest side. And so what we notice here from looking at this example is that the larger angle seems to correspond to the larger side length. So that's what we're noticing so far. Now if we look at the next triangle below, the right triangle, well, this is going to be the 90-degree angle here. So we know that's 90 degrees. So that's going to be larger than these other angles. Now the next, the other angle that we have here, this one looks, if you zoom in on that one actually looks smaller than the other angles. So this looks smaller than this one. So looks like the biggest angle is C, the second is second biggest is A, and then we have the smallest being B. All right, and those angle measures are given below, 60 degrees and 30 degrees. Now if you look at the side lengths, similarly to the top triangle, we can see that C is actually the hypotenuse in this triangle, and so C is the largest side, and then the second largest side seems to be A, the smallest side is B. And so you can definitely see there's a relationship between the size of the angle and the side length. The larger angle corresponds to the larger side length, and so on. The smallest angle corresponds to the smallest side length. And so this is related to the theorem, which I'll call Theorem 5.4.1. This is from the lesson 5.4. It's first theorem and actually given in the book that doesn't really have a name. So if two sides of a triangle are not congruent, then the larger angle lies opposite the longer side. So like we were saying earlier, since if B is greater than A, which it is in this diagram, you can see that B is longer than A, like the side length is greater, then that means that if you were to go in the opposite angle, this angle B, is going to be greater than angle A. And this inequality basically, so if you look at this convention for when we do triangles, the convention is that the capital letter indicates the vertex of the angle, and the lowercase letter is on the side that is opposite the angle. So notice that we have a capital B here for this angle, and then opposite that side is a lowercase b. For this vertex here, we got angle A, and opposite that angle is lowercase a. And therefore, because we know that there's a relationship between the opposite side and the angle, then we know because of that relationship, we can use this convention. And this is why when we use this convention, we use the lowercase version and the uppercase version on opposite sides of that triangle, and this is why. All right, so now that we went over that theorem, we're going to, and this should say Theorem 5.4.1. So we want to be able to prove Theorem 5.4.1. So in order to prove it, what we want to do is, well, we're going to do a two-column chart here. And we know that the first statement is always the given statement. So we're given that AB is greater than AC, and AC, this line segment AC is congruent to line segment AM, and therefore we have these tick marks here. All right, so, and notice also that on this triangle, we kind of drew a dashed line here, and we labeled angles 1, 2, and 3. That's going to help us prove this theorem. So the first thing that we're going to do after the given statement is realize that because AM is congruent to AC, we have here an isosceles triangle. And because we have an isosceles triangle, we can use the theorem, the isosceles triangle theorem, that states that because you have an isosceles triangle, these two sides are the same. That means the opposite angles are the same. And therefore, that means that the measure of angle 1 is equal to the measure of angle 2, given by the isosceles triangle theorem. Now, the next thing we're going to do is we're going to use the fact that if we add that we can add angles 2 and 3, and that will actually give us angle C, which is also known as angle ACB. So if I add angles 2 and 3, that's going to give me ACB, and that's known as the angle addition postulate, adding two angles to get a bigger angle. The reason why we want to use that is we're going to be using that eventually to show this relationship with inequalities. So what we're going to do now is, with that angle addition postulate, because we know that ACB is equal to those the angle 2 plus angle 3, we're going to use a property known as the comparison property of inequality. Now, this is the first time we've used this in the lessons that I've discussed. So let's go ahead and discuss that property. The comparison property of inequality states that if A is equal to B plus C, and C is a number greater than 0, then A has to be greater than C. All right, so let's look at a quick example. If A is 9, for example, and we have B plus 1 on the other side, then if C is 1, meaning C is greater than 0, right? If you look at C here, and A is 9, well, that means that B has to be smaller than 9 because 8 plus 1 is going to be 9. All right, and if C were 2, then B would have to be 7 because 2 plus 7 is going to give us 9. So you notice that as C grows larger, B grows smaller, and therefore A is always going to be larger than B in this case. This should say A is larger than B, not A is larger than C. All right, so this is how the inequality works. As long as C is a positive number, then A is always going to be greater than B in this relationship. All right, so now we're going to go ahead and use that to prove Theorem 5.4.1 using the comparison property of inequality, because we know that, so if we look at our example, if A is equal to B plus C, then that means that, and this should actually say an equal sign, not a congruent symbol. Should be an equal sign. But if A is equal to B plus C, and C is clearly going to be greater than 1 because there's no way that angle 3 is 0, then that means that A has to be greater than B, which is exactly what we stated here with our comparison property of inequality. All right, so now what we're going to do is we're going to use the substitution property, because we know that angle 2 is equal to angle 1, or rather, yeah, so we know that angle 2 is equal to angle 1, and so therefore we can replace angle 2 with angle 1 using step 2. So that's a substitution property. And then next we know that by the exterior angles property, angle 1 is equal to angle B plus angle 3, the measure of angle B plus the measure of angle 3. So if you remember, the exterior angles theorem is, well, if you look at this triangle right here and you extend this side, well, this right here is an exterior angle, and remember that the exterior angles theorem states that to find the exterior angle, you simply have to add the remote interior angles, and those are the remote interior angles, the angles that are the farthest away from that exterior angle within this triangle. And so therefore, by the exterior angles theorem, B plus angle 3 is going to give us angle 1. All right, so why do we use this theorem? Well, because now we want to again use the comparison property of inequality. Because we know that angle 3 is not 0, So this is not equal to 0, then that means that by the comparison property, angle 1 has to be greater than angle B. All right, so now what we're going to do is we know that ACB, the angle ACB, is greater than angle 1. So we got this part right here. But we also know that angle 1, if we use this step number 7, we also know that angle 1 is greater than the measure of angle B. And if that's true, if this is greater than angle 1 and angle 1 is greater than angle B, well then this also implies that the measure of ACB is greater than the measure of angle B. And therefore that's what we got in step 7. Or step 8 rather, and that's the transitive property of inequality. So for example, if A is greater than B, B is greater than C, A is greater than C. If A is greater than 5 and 5 is greater than 3, then A is greater than 3, as a simple example. And therefore, we went ahead and we proved the theorem 5.4.1. All right, so now let's next discuss the converse of the previous theorem that we just the previous theorem, which is the reverse. So remember that when you reverse the logic in a given theorem, that's known as the converse. And so remember that the previous theorem was that if B is greater than A, then that means that the angle B is greater than angle A. So now the converse is going to be if the measure of angle B is greater than the measure of angle A, then that means that B is greater than A. So the longer side lies opposite the larger angle. So this is simply reversing what we just discussed. Now, if we want to prove this, what we're going to do to prove the converse of this theorem is we're going to prove this indirectly. We're going to do it by contradiction. So remember that to prove something by contradiction, you have to assume that the opposite, you have to assume that whatever the conclusion is of the theorem, you want to assume that it's opposite. So you want to say that, okay, it's not going to be greater than A. We're not concerned with it being greater than A. We're actually concerned with it being less than or equal to A. So let's assume that it's going to be less than or equal to A. Well, then this means that B is less than A or B is equal to A, either one of those, right? So we're going to take the first case where B is less than A. Well, if B is less than A, then that means that B, angle B, has to be equal to congruent to angle A by the isosceles triangle theorem. So remember that what we just discussed with the isosceles triangle theorem, if the two sides are the same, then the two opposite angles have to be the same. But we know that this is a contradiction. This contradicts the initial assumption from the theorem that B has to be greater than A. The angle B has to be greater than A in the theorem. So therefore, we have a contradiction. So far, we're doing well with proving this by contradiction. Now, what we want to look at now is the second case. What happens if B is less than A? So if B is less than A, then that means A has to be greater than B, right? So if 5 is less than 2, or if 5 is less than 7, then that means 7 is greater than 5. So if B is less than A is greater than B, then from theorem 5.4.1, the theorem that we just proved in the previous example, we know that angle A has to be greater than angle B, which is the same thing as saying angle B has to be less than angle A. Okay, so essentially, if B is less than A, then that means that angle B has to be less than angle A. But that also contradicts what we just said in the theorem in this example. The initial assumption was that angle B is greater than angle A, right? And we just showed that it was less than with this contradiction. So therefore, we do have a contradiction of sorts. And therefore, B can't be less than or equal to A. It has to be that B is greater than A. Okay, so so this is the initial assumption that I was mentioning earlier in this example. So let's look at, let me show you. So this right here was my initial assumption, and notice that every conclusion that I made using my contradiction contradicted that initial assumption, and therefore by contradiction we proved this indirectly, and therefore B is greater than A. All right, so let's look at an example relating the two theorems we just proved. So which angle is the largest in figure above for part A? Now this is a theorem 5.4.1 question. So if we know that a given side is larger than the other side, then that means the opposite angle is larger. So since we know that this is the largest side, that means that the angle opposite of it, which is angle K, has to be greater than either angle M or angle L by theorem 5.4.1. So the largest angle here is angle K. Now the problem B on the right side, you're given an angle. So this right here is the converse of theorem 5.4.1. So which side is longest? Well, first off, we can figure out the third angle by using the triangle angle sum theorem, because we know all the angles have to add up to 180 degrees. So 50 plus 62 is 112. And we can say 180 minus 112, that's going to give us 68 degrees. And so now we can confidently say that this angle is 68 degrees. Now, because this angle is 68 degrees, that is the largest angle here, which means that if angle K is the largest angle, that means that the side opposite of angle K is the longest side in this triangle. And so the side that is the longest is side LM, line segment LM. All right, you can also say the length of the LM is lowercase k. All right, so let's investigate triangle side inequalities. What we want to do is we want to build several triangles. So let's use these building blocks to develop a triangle. So if we want to construct a triangle from these three pieces, remember we only need three sides to construct a triangle. So if I have a side of 5 meters, let's say, I have another piece that's 12 meters, and then a final piece that's 13 meters, can we construct a triangle from this? So let's go ahead and construct a triangle. Let's piece those together. So we piece the 5 and the 12 piece together, and then we will put the 13 meters together. Now we have all three pieces, and you can see that we clearly form a triangle. In fact, this is actually a right triangle. And the reason we know that it's a right triangle is that it follows the Pythagorean theorem, 5 squared plus 12 squared equals 13 squared. So in fact, this is a right triangle. So if we have these three pieces, 5, 12, and 13, we can definitely form a triangle. Now let's look to see if we have a 5-meter piece, a 12-meter piece, and a 16-meter piece, can we construct a triangle? So let's switch the 16-meter piece with the 13-meter piece, or let's switch the 13 with the 16 actually. So let's remove the 13-meter piece and replace it with the 16. Can we construct a triangle in this case? All right, so we're going to have to slightly move the two pieces earlier so that we can rearrange them and make this triangle, because the 16-meter piece is longer, and so we'll have to accommodate it. So now let's go ahead and adjust the 16-meter piece, and therefore now you can see that the pieces fit together to form a triangle, albeit it's a weird triangle. It's an obtuse triangle. You can tell that this angle is really large. And it's not quite 180, but it's pretty large, and therefore it makes an awkward looking triangle. However, this is still a triangle. It's an obtuse triangle. We're pushing the limits to how long that third side can be. Now let's look at another example, a 5, a 12, and a 20-meter piece. So before we had a 16-meter piece, and now we're going to have a 20-meter piece. Let's piece those together. Put the 5 and the 12 together. And then we'll put the 20-meter piece. And you see that there's really not much that we can do here. Even if I've basically rotated the 12-meter piece so much, and it still cannot fit the 20-meter piece perfectly in order to make a triangle. There's no way that we can put these three pieces together to form a triangle. Unlike the previous two cases, there's no way. So let's go ahead and analyze these three triangles that we constructed earlier. Can we form a triangle? Well, the first example, when we had a 5, 12, and a 13, they could fit as a triangle. 5, 12, and a 16, yes, that can form a triangle, even though it's a weird triangle. And the third example, the most recent example, we cannot make a triangle out of this. So what's the relationship between these three, the side lengths of these triangles? Well, how can we tell if we're given three pieces whether we can form a triangle or not? Well, notice that if I add the 5 and the 12 piece together, I get 17. So 5 plus 12 is 17, and 17 is greater than the third piece. Now looking at the next example, 5 plus 12 is 17, just like it was before. We didn't change anything except for that third side. And notice that third side is now 16, and 16 is still going to be smaller than if you added 5 and 12. Then, when we switch to 16 with a 20 meter piece, it failed to create a triangle, and that's because 5 plus 12 is 17, and 17 is less than 20. So you can see that if you add two of the sides in the triangle, the sum should be greater than the length of the third side. Otherwise, you're going to have issues like we did in this example. All right, this investigation, this setup that we had is illustrates what we call the Triangle Inequality Theorem, which states that the sum of the lengths of any two sides of a triangle is greater than the length of the third side. So if we're given any triangle or any three pieces, in order to make the triangle, we need to add each set of two pieces together. And when we add the sets of two pieces together, it should always be greater than the third side. So A plus B has to be greater than the third side C. A plus C has to be greater than the other side B. And B plus C has to be greater than the other side A. So for example, in the first example, when we piece together a triangle, notice that 5 plus 12 was 17, and that's greater than the third side 13. And then 5 plus 13 is equal to 18, which is greater than the other side 12. And then 12 plus 13 is greater than the other side of 5. And so therefore, as long as all these inequalities holds true, then we can make a triangle, any kind of triangle. All right, so which of the following sets of segments could be the sides of a triangle? So again, using the Triangle Inequality Theorem, so let's looking at set 1 over here on the left. If we were to add 19 plus 18, that's going to give us 37. Remember, by the Triangle Inequality Theorem, that has to be greater than the third side. But this is actually less than 40. This is actually less than the other side, which means that you cannot make a triangle out of this. This is not going to work. So we cannot form a triangle from set 1. Now, if you look at set 2, if we add 33 plus 37, that's going to give us 70 meters in this case, which is greater than 66, so that checks out. If we were to add 66 plus 33, that's going to be 99, which is greater than 37, so that checks out. And then lastly, if we add 66 plus 37, that's going to give us 83. Actually, it's going to give us here, it's going to give us 103, which is greater than 33 in this case. All right, so all these inequalities hold true, which means that we can form a triangle from those three line segments. All right, guys, that's it for the video. I hope you learned something from this, and as usual, I'll see you in the next one.